Okay, welcome back, and we're picking up where we left off, which is h. So we're looking at h, and in h we've got integral of 4 over x, the ln of x, the power 5 dx. Now, recognition plays an enormous part in mathematics at this level. Calculus mathematics requires us to have a wonderful sense of intuition built around a good recognition of parts. Now, here we can see that this has got to be a differential, and it's not obvious, but if you know that the differential, the ln of x is 1 over x, ta-da, we've got it. And if you're good enough to just write the answer, wonderful for you. But for the rest of us mere humans, let's just continue on. So u will be equal to the ln of x. We're going to stay in the column. We're going to ask the question du dx, and du dx is for the ln of x, ta-da, 1 over x. Wow. That was pretty straightforward. So after a bit of manipulation algebraically, we get to du equals 1 over x dx. We've stayed in the column and we've come to look for this. Now this 4 can come out the front, so I can make it completely obvious to you. Some of you won't need this, but some of you will be grateful for that simple step. And so it's all about training and education that leads to intuition and recognition. Okay, so here, are you there? Yep. Are you there? Yep. So you're both gone, and you're both gone by du. Wow, look at that. Just like that, the power of our integration, and we had a 4, so we'll maintain that. The power of our integration is that we've been able to make a serious and significant substitution and depower an ugly, complex-looking integration to a simple, easy up and under. So we'll do the trivial substitution. That's the one that you don't want to be rushing to because you stayed in the column. Okay, stay in the column. Finish your substitution on the column, then you can come and do the simple stuff. Okay, so hopefully I'm impressing on you the importance of that. So the integration will become up and under over 6 plus a capital C. Also what we recognise is that that's 6. Let's just clean that up. And a 6. Alright, so we've got cancellations we can make there. 2 goes into that twice. 2 goes into that 3 times. And so finally we can say 2/3 to the power 6 plus C, and putting our substitution back in, ln of x. So we've been able to do a tremendous amount of work taking a complicated integration and simplifying it. And that's what we're about. That's what we're about managing. So in that regard, we're doing well. Okay. All right. So let's keep moving on. The integral of e to the x. So by recognition, we're looking for to build our intuition, e to the x, and we've got in the bracket e to the x plus 4. Can you see the differential yet? Okay, if I'm doing my job, have you been able to see the differential? Okay, so if we let the internals of the bracket e to the x plus 4 equal u, then du dx will be equal to, the 4 is a constant, so the 4 goes, and we're e to u, that's the one we love, it's so cool, e to the u, e to the x. Very good. So du, with a bit of manipulation, is equal to e to the x dx. Okay, very good. Are you there? Yep. You get sick of me saying this by the end of this. E to the x, are you there? Yep. So you're gone. The power of substitution has arrived, and we just did the power of substitution. What's left is the trivial substitution that might come from a shortcut teaching or some other kind of trivialized approach to U substitutions, and so we get U3. Our integration then is a simple up and under. Up and under is a phrase that we used to use as kids on the football field. Kick it up, catch it, try. Up and under. So that's all that means. So 1/4 to the power 4 plus c, and u itself was e to the x plus 4. Wow. So we're getting through some work in doing our integrations, and it doesn't seem to matter how traumatic it is, we seem to be able to manage it. Okay? So, and they are traumatic. I agree with you. You know, sometimes I sit down and sit in front of an equation and I think, what on earth am I going to do here? And that's a perfectly natural response, isn't it? We're humans. I'm not trying to teach you to be super people. I'm allowing to, we're allowed to be humans, for heaven's sakes. We're allowed to be intimidated by mathematics. I'd much rather be intimidated by mathematics than anything else that's going on in life generally, humans and conflicts and disagreements and all the things that we have in life. I'd much rather sit down and go, oh, I've got the wobbles here. But you know what, let's try and apply a little bit of a training and see if we can't use our training to iron out the rocky road. Okay, let's see if we can't use our training to help with that. So Leibniz notation, staying in the column, not going to rewrite anything in integration. We do that in the chain rule, we don't do it here. Okay, so the differential of 5 plus e to the x is just e to the x. So how good is it? Alright, a bit of manipulation algebraically, and du is equal to it gets like an old songbook now, doesn't it? Are you there? Yep, you bet I am. Are you there? Yep, you bet I am. I'm sitting up on the top. So you're gone. You're both gone. And so what we've got is the integral. That's the power of our substitution right there. That blank, that symbol, and that du represent U substitution integration. The trivial one is this one. The trivial one is this one. Okay? Now we can do a bit of pre-work. I could have put that as a half. I could have done all of that. You're quite right. So the integral u to the half du is equal to the integral of u to the minus u. So we do up and under. U minus a half plus 1's a half, so I'm being a bit cheeky doing something in my head. Divide by a half means we're going to have times by 2 over 1. I'm not going to put the over 1. C, and that equals 2, the square root plus c, and the u was 5 plus e to the x. Wow, how good are we? Cool. You can check all of these, of course, with Wolfie, if you want to. Alright, so K, we're getting the pattern now. Look at this one. You serious, man? Man, are we going to be able to do this? Come on. Have you ever seen anything so complicated in your life? This is like a kicker. Okay, it's like a kicker. So a bit of pre-work might help. So we'll integrate sec. So I could make that a bracket like I'm going to do here and put tan x in. I could do that. There'd be nothing wrong with me doing that. But I want to use the differential. See, there's the partners, isn't it? u is tan x. And why did we pick tan x? Because the differential, see, we're being active in our response to this. Our differential of tan is sec, so we're being active in observing and recognising that the differential is sec squared, and that's going to become our substitution. Our substitution is going to be sec squared x. Wow. Okay. So this simplifies. Are you there? Yep. Are you there? Yep. So all we're left with is this is our main substitution. Dx and sec squared are gone. See how much it is when I change things a little bit? I didn't do the squiggles, did I? And I didn't ask the question, are you there yet? I just talked over it. See, that's the hard bit, isn't it? So the education training tells you, dx, are you there? Sec squared x, are you there? Yep, you're both gone. And now we've replaced you with this integral du. That was the hard work of u substitution, staying in the column. Staying in the column and doing a u substitution. Now we've just got the simple one. So the less I talk, the more you have to build, you see. The more you have to carry on your own. And so we've got tan x to the 7. Can I just write it like this? Oh, actually, I'm jumping ahead of myself. Getting all excited about substituting in. Can you do the integration first, Jason? That would be good. 8 up and under plus c. Now you can get all sloppy. So 1/8 to the power 8 plus c. And what goes in here is u and x. And yes, if you want to, you can write tan 8 x, and that's fine. You can do that as well. Okay, so either one of those is correct. Oh, that was at first a very shocking one. Okay, that was the end of question 1, by the way. So that's given us quite a bit of thinking to do. So I'll do a few out of question 2 as well. And then we're going to try and change tack. So I might just end the video here. This is a shorter one. And we'll have a look at question 2 because this has got the form. You can do u substitutions with those. You can. But I'm going to try it a different way. I'm wondering. Oh, I can continue on. Alright, question 2. We've been doing u substitutions. A variation of the u substitution is to recognise that in our integration we have the form of an equation. If the integral of the derivative sits over the function, we can just substitute the ln of the function plus c. You can do that. That's a thing. Now that's a variation of the chain rule. And to show you that, I'm going to do it both ways. Now, is the derivative of the denominator on the numerator? And the answer is no, because we need 3 on the top. So we're going to multiply this integral by 1. And that means that we will not simplify or change necessarily the integral. It's still the same integral. Okay? Now, what's the form of 1 that will be helpful? Well, the differential of 3x is 3, and 3 is not sitting on the top, so we need a 3. So the form of 1 that we're going to use is 3 over 3. Okay? And I'm just doing it step by step because I'm a long way teacher, but we could use, we're going to do the u substitution in a minute, but this now means that we can borrow this guy here, put it across the constants because we can go one way or the other according to the rule, and that means we will have 1/3 3 over 3x plus 4 dx. Now, we can ask the question again. They are equivalent. They are the same. They're all the same integrals. Looks different, like equivalent fractions look different, But we can be assured that because we've multiplied the integral by 1, we have not changed it. So, is the derivative of the denominator on the numerator? Yes. So the integration becomes 1/3 the log of the denominator. And you'll need this. You'll need this in Maths 1. Okay? I believe that it's worth teaching, because if we just leave it up to manipulating the quotient, I believe that if we just leave it up to the u substitution, you might lose your way. So let's try it anyway. Let's do let u equal 3x. And the math should always line up. There's no tricks to it. Once you do it, it should be the same. The u, the x is equal to 3. And so we do some manipulation and we'll get 1/3 du is equal to the x. Okay, so in this original integral, are you there? Yep. Well, you're getting subbed out for du 1/3. du 1/3. So we end up at the same point by using the u substitution method or using the quotient recognition model, which is a variation on a thing. Now we've still got 1/3 out the front. Now what is it? It's 1 over u. Okay, 1 over u. So what's the differential? Is the differential? And we're asking this same question yet again, but we're just doing it on a simpler form. Is the differential of the denominator on the numerator? So you're using this anyway. Yes, it is. So that's simply substituted as the ln of u. So we've got the ln of u, okay, which can only be positive, plus c, and when we put it all together, we get 1/3 the ln, and in this case u was 3x plus 4 plus c. So at some point you have to ask this question, and sometimes I think it's just as easy to do it over here in the left-hand column. So that's the way I'm going to approach this. You can do the u substitution here, okay, anytime you like. But at some point, you're still going to have to do this, okay, is the derivative on the denominator. So it's not going to be dismissed. All right, I've got time for another one. So we'll do a B. Have we got the derivative of the denominator on the numerator? No, we don't. Okay, so we need to introduce a 1. Okay, and the 1 that we're going to use is 9. I've already stolen the 9 away, so I've missed a step. Okay, and I'll put the 9 on the top. Is that now the derivative of the denominator on the numerator? Yes, it is. So we can now go straight to the substitution. Another easier form where we just take the log of the denominator. Wow. Plus capital C. Okay, so we've got a very simple form. That wasn't so it's a couple of steps. Now I put all the working steps in here. I must admit I skipped it because I expect you to understand that I brought the 9 over from the 1/9. I brought the 9 over. 9 over 9 is 1. 1 times the integral doesn't change it. So little variations of that can occur. And this one's a good one to consider because it's asking for the integral of 3 7x plus 2 is the derivative of the denominator on the numerator. No, it's not. So we're going to take that 3 over the front. Okay, so we're going to have 3 times the integral, because you're allowed to do that by the constant moving rule. That leaves us with 1 is the derivative of the denominator over there. No, it's not. So we can't invoke this yet. We have to multiply by 1. And the form of 1 we're looking to do is 7 over 7. So we'll borrow the 7 and put it up on the top, and we'll be left with 3 over 7. So the integral will be 3 over 7. The derivative is now, yes it is, because we've now put a 7 on the top. 3 on 7, integral 7, there's our 1 in disguise. 7x plus 2 is the derivative on the top. Yes, it is. So we can go straight to the integral, which is 3/7 the ln of 7x plus 2. Don't forget your plus capital C, because otherwise it's wrong. Okay, so we were able to do that. All right, that's about 20 minutes, so I'll pause there and I'll be back with the next video.